Good afternoon, everybody. Zekeriya Erkin from Delft, University of Technology. It's a collaboration of multiple people, as you can see, but they didn't want to come here, breaking up their summer holiday. So the pleasure is on me to be with you. The topic is data aggregation, privacy preserving and secure. Data aggregation has been a very important topic for the last couple of decades, and it appears in different domains. Maybe you know about smart grids, where you need to balance the load or predict the usage consumption. It's very important for medical data, statistical analysis on medical data as well. But if you think about it, data aggregation is a core component in many domains, especially in signal processing, recommender systems, clustering, and in general, machine learning. There are several reasons where we want to have secure and privacy-preserving data aggregation, because the data is coming from individuals mostly, which are pretty much privacy-sensitive data. And we have GDPR-related issues, as you might imagine in Europe, and HIPAA-related considerations, restrictions in the United States, that data aggregation should be done in a proper way. What is very interesting is that the related work in this field always assumes a trustworthy, semi-honest aggregator. This aggregator is honest enough to collect the data and aggregate them, but never tries to destroy the protocol. And the basic assumption is, because of reputational reasons or economical reasons, aggregators are always thought trustworthy. I'm afraid in real life this is not the case. In many cases right now, especially in machine learning, we see that aggregator is not trustworthy either. So what is the general construction? We need to have a verifiable data aggregation protocol. Most of the time, people prefer homomorphic crypto systems or multi-party computation. The inputs are collected from, for example, smart meters. An aggregator collects and aggregates the data with verification in terms of signatures can be calculated easily. This is properly done in many works. There are a lot of works in this field. However, the issue is as follows. If the aggregator is corrupt or not fully trusted, there's no way we can verify the total sum, aggregated sum. Because after collecting the signatures from the users and after collecting the aggregate data, the aggregator can change the signature or even report the wrong output. So this is what's happening in the literature, and we only identified 3 works to come up with a solution. Those 3 works considers different scenarios. The most elegant one, to our knowledge, is a work from 2021 that splits the trust between an aggregator and a converter. So it's assumed that the converter is fully trusted, so there's a split of work, and they only enable a pairwise collusion between any user and the aggregator and the converter. This is a very elegant solution. It works, but there's a flaw in the protocol. You can find it in the paper. If the user provides a special value, that value can be used to construct any, forge any signatures by the aggregator. Hence, we come with an idea to design a publicly verifiable data aggregation protocol based on the secret input. What we want to have is confidentiality. The input will be kept secret from the aggregator. Integrity and authenticity of the aggregate sum is necessary. And we want to have a malicious aggregator in the protocol. So not fully trusted, semi-honest or so, a malicious aggregator with a number of malicious users in the system. So as far as we know, this is a very realistic construction needed in practice, and we also don't want to have any trusted entities during the execution of the protocol. This is our goal, and for this, this is the summary where we can show the adversarial model. As you can see, we can have one or multiple verifiers. We have an aggregator, multiple users. We only need a trusted entity for the setup phase. I'm afraid in cryptography we have assumptions, and this is our assumption. For setup, we really need a trusted entity. After the setup, this entity will leave the protocol and never be seen again. In our work, we have 4 protocols. The basic protocol is MPAS. It's the verifiable aggregate signature with malicious participants. You will see that it has multiple interactions with the users. Thus, we came up with another version, MPAS Plus, that groups the users such that we have less communication needs. We also have MPAS-IV, which is actually detection and removal of the malicious users, because when you have signatures, you can also verify the inputs if they are correct or not using zero-knowledge proofs. And that can be used for very specific applications, especially in medical domain. And we have one final protocol that I will not be able to explain. When you have malicious entities, users, you can detect them and remove them, but you don't need to restart the protocol. So those variants, we find it very interesting, and to be honest, they are all chosen from a European Union project called Septon. They will be actually implemented and deployed in practice for medical data. Now, I will try to give a very high-level illustration of how the basic protocol works. This is our goal. Every round, the users will provide some kind of a sensitive data, which is represented by X. That round will be T. It is coupled with a hash value. The secret or the signature of the users will be in this format, where and secret components should be provided by each user. This is a general construction. When you have this from every user, the total should have something like this. The total signature should combine all the values from different users plus the secret values from individuals. This construction, you can see many works, but this is not sufficient for us, because this construction can be abused by the aggregator, because there's nothing hiding this value, the signature, from the aggregator. Thus, we need to wrap it with a secret value S, which is hidden from the aggregator. So, and if you want to be robust against malicious users, what would you do? You can deploy Shamir's secret sharing. So this is actually the main idea. Creating a joint signature from the users wrapped with a signal, with a secret value from the aggregator, and use secret sharing, Shamir's secret sharing, to make it robust against different numbers of malicious users. Let's go over this maybe in a very fast pace. The setup phase is all involved with the trusted dealer, which is the green box here, T. It has a secret value S from the ZP, and this is split into N parts. This is the number of users in the system. We also assume that there are at most K malicious users, so we also need to use K+1 out of N Shamir secret sharing. Each user will produce their own private secret. This will be reported back to the trusted dealer, such that the trusted dealer will create the verification key to be given to the verifier. If you take a look, there's nothing secret about this. Secret values from the users wrapped with the secret value S against the aggregator. This value will be given to any verifier. Later on, the trusted dealer for every individual will create K+1 secret values. This is for Shamir's secret sharing for each verifier. This will be used as a masking value, but they will be constructed in a special way. All values added up should end up with a 0 value. So this is the nice construction about masking the values of every individual signature. Together with the S, the shared value of S, and the E values, the users will have a private set of integer values. And during the signing phase, of course, the signature will be constructed by using these parameters, sent to the aggregator. Aggregator cannot change this format because any change will result in a malformed final signature, so the protocol will abort. So that's very good for us. Aggregator will send this value to k different users. It can be chosen randomly, but for the sake of simplicity, let's say the next k users. K users will mask and add their values and add their signatures. This is pretty straightforward. If you think about it, they should be providing their input for the user, and for that they need a mapping. For every user, they have a different value, integer value produced in the system. They should remember this value. Together with the wrapping value s, they will return these values to the aggregator. Aggregator will multiply, but there will be one value missing from the first user who initiated signature. With the addition of this user's part, we will end up in a very nice signature in a way that we can construct the signature with k malicious users in the system. Thus, we achieve our goal for the signing phase, and this aggregator will provide the final signature wrapped with the secret value s to the verifier. And if you take a look at the construction, it's very straightforward. The Shamir secret share will create the value s, and the total of the e values will add up to 0. There's only one catch. This is only one signature for one user. So this will be repeated for all users in the system, which is hence the communication-wise very demanding. But at the end, the verifier can easily verify this statement, the signature is correct or not, because the verification keys will satisfy this equality. So we are also using bilinear maps, as you can see. The data provided by the aggregator will be satisfied if everything goes okay with the verification key that the verifier has. This is in a nutshell the basic protocol. The other three protocols add up to this one by one in terms of reducing the communication cost, detecting the malicious users and removing them from the system, and detection and deletion should not stop the protocol. I really strongly suggest you take a look at the paper for details, but what is very interesting for me, being in this field for almost 2 decades, the results, experimental results for something like this is very, very good. Why? On a single core computer with no optimization whatsoever, including parallelization, the results are less than half a second for almost 1,000 users in the system. For generating signatures, aggregating and verification, numbers are pretty much good. So this is very good because this is usable security, and we can deploy this in practice. And compared to state-of-the-art, our numbers are justified by the complexity analysis. The numbers are depending on the number of users and the malicious number of malicious users, k, and if you apply grouping, the group size, c. That's very good. So in a nutshell, my time is up. We provided confidentiality and integrity for publicly verifiable data aggregation, which is an essential component for many protocols. And we have robustness against collusion between aggregator and malicious users. With this, I want to thank you all for your attention, but I also want to thank the anonymous reviewers. Actually, they improved our work significantly. The first version was with a security flaw, and we managed to fix it thanks to them. So thank you very much.